So this is lecture 25, number theory. And then when I want to
When
go,
are you going to upload the review for the exam?
so there's the review. The only thing we've done since the last exam is primitive roots. So the review is the review for the first exam plus the review for the second exam plus this homework on primitive roots. There does not need to be a separate sheet because there's nothing new other than the beyond primitive roots from the first two review sheets.
Oh, okay. I thought you were gonna like select couple of problem from each exam and stuff and put in one sheet and have a review.
Well, I mean, it's the same thing. I mean, the exam covers the material in the course, and most of that's on the review sheets, but anything in the course can be on the final exam.
Okay.
So we want to find a primitive root mod 23. And the simplest thing is just to experiment to try g equal 2, 3, and so on until you find a primitive root. So
Last time you said 2 wasn't a primitive mod
I'm
20.
solving the problem from the beginning,
Yeah.
right? So in the beginning, you start with 2. If 2 doesn't work, then you go to 3, right? So this isn't intended, what I'm doing right now is not intended just for you. It's intended for any student in the class who watches the lecture. So we start with g equal 2. In general, a primitive root mod 23 has order 23 minus 1 or 22. And the order of every integer a such that a is relatively prime to 23 is a divisor of 22. So 1, 2, 11, or 22. So if an element does not have order 1, 2, or 11, then it must have order 22, and therefore it's a primitive root. So let's try g equal 2. 2 to the first power is 2, which is not 1 mod 23. 2 squared is 4, which is not 1 mod 23. So then we have to calculate 2 to the 11th power. So we can do that any way we like. We could 2 to the 11th is what? 2 to the 11th, I think, is 2048. 2 to the 9th is 512. 2 to the 10th is 1024. 2 to the 11th is 2048. So you just have to divide 23 into 2048. And this goes how many times? 8 3s are 24. 8 2s are 16 and 2 are 18. That's 2,208. 23 into this goes 9 times. 9 3s are 27. This leaves a remainder of 1. So 2 to the 11th is congruent to 1 mod 23. So the order of 2 is 11, which is not 22. So 2 is not a primitive root. So the next number to try, you can try any number that you like. You could try 3, 5, 7, or 1,000,000, but I prefer small numbers, so I'll try g equal 3. 3 to the first power is 3, which is not 1, mod 23. 3 squared is 9, which is not 1, mod 23. Now I have to calculate 3 to the 11. What is that congruent to, mod 23? Well, I could just take 3 to the 11th power and divide by 23. Perfectly fine way to do that. Or I could use some other method. For example, 3 cubed is 27, which is 4 mod 23. So 3 to the 6th is 3 cubed squared is 4 squared is 16 mod 23. And then 3 to the 9th, let's see, what is 3 to the 9th? That's 3 cubed times 3 to the 6th. That's 4 times 16. That's 64 mod 23. That's the same as minus 5 mod 23, because 69 is 3 times 23. 3 to the 11th is 3 squared times 3 to the 9th. 3 squared is 9. 3 to the 9th is minus 5. That's minus 45. That is congruent to 1 mod 23. So the order of 3 is also 11. So 3 is not a primitive root. So we have to keep trying. After 3, we could try 4, but we know that 2 to the 11th is congruent to 1 mod 23. So 4 to the 11th is 2 squared to the 11th, is like 2 to the 11th squared, which is 1 squared, which is 1 mod 23. So the order of 2 is also 11. Sorry, the order of 4 is also 11. So 4 is not a primitive root. So then we try g equal 5. So 5 to the first power is 5. 5 squared is 25, which is 2. It's not 1. Mod 23. So 5 does not have order 1 or 2. Let's see. 5 to the 11th power. 11 is 2 times 5 plus 1. So this is the same as 5 squared to the 5th power times 5. 5 squared is 2. So this is like 2 to the 5th power times 5, which is 32 times 5. 32 is 11 mod 23. So this is 11 times 5, which is 55. Let's see. Let me just double check if something doesn't look. Oh, 32 is not 11. 32 is 9 mod 23. 9 times 5 is 45. 45 is minus 1 mod 23. So the order of 5 is not 1, 2, or 11, which means it has to be 22. So 5 is a primitive root. Mod 23. So this is not the only primitive root. There are other primitive roots, but the problem was to find one. And that's what we just did.
Why we didn't try 4 to the 22?
Sorry?
Why we didn't try, we did 4 to the 11, why we didn't try 4 to the
So
20?
4 to the 11th is 1. So that means the order of 4 is 11. The order is the smallest power of the number congruent to 1. 4 to the 11th is congruent to 1. That's the smallest power. So the order of 4 is 11.
Okay, and 4 is not a primitive root?
because the order is 11. A
Oh, okay.
primitive root has order 22.
Okay.
Every number to the 22nd power is going to be 1 mod 11, but the question is, what is the smallest power? Okay. Let's look at problem 2. We want a primitive root mod 41. So 41 minus 1 is 40, and 40 has a lot of divisors. 1, 2, 4, 5, 8, 10, 20, and 40. So every number that's relatively prime to 41 or not divisible by 41 has an order in this set, and a number relatively prime to 41 is a primitive root if it's smaller, if its order is 40 and not one of these smaller numbers. So again, we can try 2. 2 to the first, everything is mod 41. 2 to the first power is 2. 2 squared is 4. 2 to the fourth is 16. 2 to the fifth is 32. So we can cross, so 2 does not have order 1, 2, 4, or 5. What about 2 to the 8th? Let's see, what is 2 to the 8th equal to? 2 to the 8th is 64. Sorry, not 64, 256. So I could divide 256 by 41. Well, that's one way to do it.
4.
41 into 256 goes 6 times. So 2 to the 8th is congruent to 10 mod 41. What about 2 to the 10th? 2 to the 10th is 2 squared times 2 to the 8th. 2 squared is 4. 2 to the 8th is 10. 4 times 10 is 40, is congruent to minus 1 mod 41. So 2 does not have order 10, but 2 to the 20th is 2 to the 10 squared, is minus 1 squared, is congruent to 1 mod 41. So 2 has order 20. So it's not a primitive root. So we have to keep trying. Let's try 3. Suppose, so we want to compute the order of 3 modulo 41. So 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. 81 is congruent to minus 1 mod 41, because 82 is 41 times 2. So 3 to the 8th is 3 to the fourth squared. It's congruent to minus 1 squared, which is plus 1 mod 41. So the order of 3 is 8. It's not 40. So 3 is not a primitive root. We can also exclude 4 right away because we saw that 2 to the 20th is congruent to 1 mod 41. So 4 to the 20th, which is 2 squared to the 20th, which is the same as 2 to the 20 squared, which is then 1 squared, is 1 mod 41. So 4 is not a primitive root. So you can try g equal 5. 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. Let's see. 41 times 3 is 143. Is that right? Sorry, is 123. So 125 is congruent to 2 mod 41. 5 to the 4th is 5 times 5 cubed is congruent to 5 times 2, which is 10 mod 41. Five to the 5th is, I don't know, 5 to the 4th times 5, which is 10. 5 to the 4th is congruent to 10 times 5, which is congruent to 50, which is congruent to 9 mod 41. So 5 does not have order 1, 2, 4, or 5. What about 5 to the 8th? 5 to the 8th is 5 cubed times 5 to the 5th. 5 cubed is 2. 5 to the 5th is 9. This is 18 mod 41. So 5 does not have order 8. 5 to the 10. What's 5 to the 10? 5 to the 10 is, well, let's see, I don't know.
5 to the 8 times 5 squared.
Okay, 5 to the 8th times 5 squared. 5 to the 8th is 18. 5 squared is 25. That's going to be too big, so that's correct, but let's see if I can make an easier way to do it. How about 5 to the 10th is 5 times 5 cubed, because this is 5 to the 9th, times 5 is 5 to the 10th. 5 cubed is 2, so that's 5 times 2 cubed, which is 5 times 8, which is 40, which is minus 1 mod 41. So 5 to the 20th is 5 to the 10 squared, is minus 1 squared, is 1 mod 41. So 5 does not have order 1, 2. These are the excluded orders. 5 doesn't have order 1 or 2 or 4 or 5 or 8 or 10
Or 20.
But it does have order 20. So
But it's not
5
a
is
primitive
not a primitive root.
Wait a minute.
Let's see. So we could even make a little table so far of what we've calculated. So for different numbers G, and then the order of G, mod 41, we just looked at 2, 3, 4, and 5. So 2 had order 20. 3 had order 8. 4 actually had order Back when I was looking at 4, I could have actually have said the following. 4 to the power 10 is 2 squared to the 10, which is 2 to the 20, which is 1 mod 41. So 4 actually has order 10. What about 5? 5, we just saw, has order 20. What about 6? Sorry, what about 6? We don't know the order of 6. So let's try G equal to 6. So 6 to the first power is 6. 6 squared is 36, which is the same as minus 5 mod 41. So 6 to the fourth, which is 6 squared squared, is minus 5 squared is 25 mod 41. What about 6 to the fifth? 6 to the fifth is 6 times 6 to the fourth. That's 6 times 25. That's 150. What's 150 mod 41? So 3 times 41 is 123. So this is 17 mod 41. No, sorry, 27 mod 41. Because 150 minus 27 is 123. So 6 to the fifth is 27. Or minus 14, if you like, same thing. What about 6 to the eighth? 6 to the eighth is let's see, 6 times 6 squared times 6 to the fifth. So that's 6. 6 squared is minus 5. 6 to the fifth is minus 14. So this is 6 times 70. 82 minus 70 is 12. Or let's say this is the same as 420. If you divide 41 into 420, this goes 10 times and leaves a remainder of 10. So 6 to the eighth, if I did this arithmetic right, is congruent to 10 mod 41. 6 to the 10th is 6 to the eighth times 6 squared. 6 to the eighth is 10. 6 squared is minus 5. That's minus 50, which is minus 9 mod 41. 6 to the 20th is 6 to the 10 squared. That's minus 9 squared. That's 81. That's minus 1 mod 41. So if you're looking for the order of 6 mod 41, it doesn't have order 1 or 2 or 4 or 5 or 8 or 10 or 20. So the only other possibility is that the order of 6 is 40, and that's a primitive root. 6 is a primitive root, mod 41. Just for fun, let's also try G equals 7. I'm curious. whether 7 might also be a primitive root. So, I mean, I can stop at this point. The problem was find a primitive root, and 6 is a primitive root. But suppose I try g equals 7.
When I
7 to the
tried,
fourth.
I got 6 is not a primitive root, but 7 is a primitive root when I solved it.
So let's see. Let's double check. 6 to the first power is 6. 6 squared is 36, which is minus 5. 6 to the fifth is 6 squared squared. That's minus 5 squared. That's 25. 6 to the fifth is 6 times 6 to the fourth. That's 6 times 25, which is 150, which is congruent to 27 mod 41. And 27 is minus 14. 6 to the eighth is 6 times 6 squared times 6 to the fifth. That's 6 times minus 5 times minus 14. That's 6 times 70, that's 420, which is 10 mod 41. 6 to the eighth is 10. 6 to the 10th is 6 to the 8 times 6 squared. 10 times minus 5 is minus 50, which is minus 9. 6 to the 20 is 6 to the 10 squared, is minus 9 squared is 81, which is minus 1. So 6 doesn't have order 1, 2, 4, 5, 8, or 10, or 20, so it must have order 40. So this is correct. 6 is a primitive root. So you just need to double check your calculations. Let's try g equals 7. 7 squared is 49, which is 8 mod 41. So 7 to the fourth is 7 squared squared, which is 8 squared, which is 64, which is 23 mod 41. 7 to the fifth is 7 times 7 to the fourth. That's 7 times 23. That's 161 modulo 41. See, 4 times 41 is 164. So 161 is minus 3 mod 41. 7 to the eighth power is
Can you move the paper up? I can see.
7 to the eighth power is 7 times 7 squared times 7 to the fifth. That's congruent to 7 times 8 times minus 3, which is 56 times minus 3. 56 is the same as 15 times minus 3. Is minus 45 is minus 4, not 41. 7 to the 10th is 7 squared times 7 to the 8th. 7 squared is 8. 7 to the 8th is minus 4. So that's minus 32, which is the same as 9. So 7 to the 20 is 7 to the 10th squared, which is 9 squared, which is 81, which is minus 1 mod 41. So 7 does not have order 1 or 2 or 4 or 5 or 8 or 10 or 20. All that's left is 40. So 7 also has order 40. Seven also has order 40. So 6 and 7 are both primitive roots mod 41. Right? So primitive roots are not unique. So we just found two different primitive roots. Mod 41. Problem 3 is to show that 2 is a primitive root mod 101. So we want to look at the powers. 2 to the first is congruent to 2. 2 squared is,
problem 3 was not part of the homework.
oh, I'm going to do it anyway. It's fun. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. See, the 101 minus 1 is 100. And what are the divisors of 100? 1, 2, 4, 5, 10, 20, 25, and 50. And 100, of course. So every element mod, every integer mod 101 has an order which is one of these 9 numbers. So 2 doesn't have order 1, 2, 4, or 5. So we can cross those off. 2 doesn't have order 1, 2, 4, or 5. What about 2 to the 10th? 2 to the 10th, what is 2 to the 10th? It's 1024. If you divide 101 into 1024, that leaves a remainder. 14, 0. Leaves a remainder of 14. So 2 to the 10th is congruent to 14 mod 101. Cross that off. 2 to the 20 is 2 to the 10 squared. That's congruent to 14 squared. 14 squared is 196. It's not congruent to 1. In fact, it's congruent to minus 6 mod 101. Two to the 25 is 2 to the 5th times 2 to the 20. That's congruent to 32 times minus 6. 32 times minus 6 is 192, or minus 192. And this is congruent to 10 mod 101. So we can cross 20 and 25 off the list. 2 to the 50 is 2 to the 25 squared. That's 10 squared. That's 100, which is minus 1 mod 101. So 2 doesn't have order 50. We can cross it off the list. So the only thing left is 100. So 2 has order 100, modulo 101, and 2 is a primitive root. And you need to know 2 is a primitive root in order to solve problem 4. We want to compute the index of 25 with respect to the primitive root 2. So to say, call this number k means that 2 to the k is congruent to 25 mod 101. So we want to find the smallest non-negative integer k such that 2 to the k is 25 mod 101. And How do we do that? Well, I don't think there's any efficient algorithm to do that. We'll just do it by trial and error. Let's look at the powers of 2. We already have some powers of 2. 2, 4, 8, 16, 32, 64. What about 2 to the 7th? 2 to the 7th is 128. That's congruent to 27 mod 101. 2 to the 8th is 2 times 2 to the 7th. 2 times 27 is 54 mod 101. 2 to the 9th is 2 times 2 to the 8th, which is 2 times 54, which is 108, which is congruent to 7 mod 101. Not there yet. 2 to the 10th is 2 times 2 to the 9th is 2 times 7 is 14. 2 to the 11th will be 2 times 14 is 28. 2 to the 12th will be 2 times 28, which is 56. 2 to the 13 is 2 times 56, which is 112, which is 11. Well, might take a while. I don't know. 2 to the 14 is 2 times 11. 2 to the 15 is 2 times 22. 2 to the 6th is 2 times 44. Sorry, 2 to the 15th is 2 times 2 to the 14th. So we're not even close to 25 yet, right? We want to find, we're not close to 20. I'm sorry, compute the index of 27.
Yeah.
Oh, then I was done right away. 2 to the 7th is 128, which is 27. So the answer is the index of 27 is equal to 7. I didn't need to do all this other work, right? 2 to the 7th is congruent to 7. No, yeah, sorry. I'm looking for the index of 20. Yeah, the index of 27 is 7. That's exactly right. Because 2 to the 7th power is 128, which is 27 mod 101. So 7 is the smallest positive power of 2, congruent to 27 modulo 101.
Okay. You wrote here 2 to the k congruent to, is that 25? You meant
Sorry?
20. 2 to the k right here. You meant 27, right?
So it means 2 to the k congruent to 27. This is what we're trying to find. The
Okay.
smallest power, the smallest positive number k, such that 2 to the k is congruent to 27 modulo 101.
Okay.
Mhm. Let's see, what about, which were the homework problems that I assigned?
You said page 7 and page 7, 1 to 10.
1 to 10.
Yeah.
Oh, okay. So I did assign problem 3.
Problem 3.
Yeah. If I assign 1 to 10, then I certainly had assigned problem 3.
No, but it's in a different page. Because the first two problem we did was on page 2. And the
So
others,
these 2 problems are on page 7. They're repeated. If you go to page 7, I just did problems 1, 2, 3, and 4 on page 7.
oh, okay.
Let's see, let's look at 2 and 3 mod 5. So 2 to the first power is 2 mod 5. 2 squared is 4 mod 5. 2 to the fourth power is 1 mod 5. 3 to the first power is 3 mod 5. 3 squared is 4 mod 5. 3 to the fourth power is 81, is 1 mod 5. So 2 and 3 are both primitive roots modulo 5. And the problem is to look for a prime. So this is part A. So find a prime P bigger than 5 for which 2 and 3 are primitive roots. So again, this is just trial and error. Start looking at the primes bigger than 5 until you find one for which 2 and 3 are primitive roots. 7 doesn't work. 2 cubed is congruent to 1 mod 7. So not 7. 7's not a prime for which 2 and 3 are primitive roots. You could try P equal to 11. So mod 11, what are the powers of 2? 2, 4, 8, 16, which is 5, 32, which is minus 1, 2 to the 6th power is, what is 2 to the 6th power? 64. 32. So, sorry. So 2 to the 5th, which is, let me not do it so quickly. Is 2, we have to answer the questions whether 2 and 3 are primitive roots mod 11. So mod 11, 2 to the first power is 2. 2 squared is 4. The divisors of 11 minus 1 are 10. The divisors are just 1, 2, 5, and 10. 2 to the 5th is 32. Which is congruent to minus 1 mod 11. So 2 is a primitive root mod 11 because it does not have order 1, 2, or 5. What about 3 mod 11? 3 to the first power is 3. 3 squared is 9.
Professor, where you get 11? You chose 11?
This is trial and error. I'm just trying. It says find a prime bigger than 5.
Okay.
What are the primes bigger than 5? 7, 11, 13, 17, 19. You just keep trying until you find one that works.
Okay.
So 7 doesn't work because 2 is not a primitive root. So we cross off 7, and the next one we try is 11. So 2 is a primitive root, but what about 3? 3 squared is 9. 3 to the 5th power is what? 3, 9, 27, 81, 243. 243 modulo 11 is 1. So 3 is not a primitive root mod 11. So we can cross off 11. Right? We're trying to find a prime for which both 2 and 3 are primitive roots. So mod 7, 2 is not a primitive root. Mod 11, 2 is a primitive root, but 3 is not. We want to find a prime for which 2 and 3 are both primitive roots. So we could try p equal 13. So mod 11, what are the powers of 2? 2, 4, 8, 16, which is the same as 3. So this is 2 cubed. What is 2 to the, 13 minus 1 is 12. And the divisors of 12, there are a lot of them, 1, 2, 3, 4, 6, and 12. So 2 to the first power is not 1. 2 squared is not 1. 2 cubed is not 1. 2 to the fourth is not 1. What about 2 to the sixth? 2 to the sixth is 64, is congruent to minus 2 mod 11. Right? Not a primitive root. So 2 does not have order 1, 2, 3, 4, or 6. Oops, sorry, can't be right. 2, I'm sorry, mod 13. I'm looking at this mod 13. So mod 13, 16 is congruent to 3. Mod 13, 64 is congruent to minus 1. So 2 is a primitive root, mod 13. What about 3? 3 squared is 9. 3 cubed is 27, is congruent to 1, mod 13. So 3 is not a primitive root, so we can cross 13 off this list. So then we look at the next prime, 17. So p equals 17. So 2 to the fourth is 16, which is minus 1 mod 17. So 2 to the eighth is 2 to the fourth squared, is minus 1 squared, is 1 mod 17. So 17 doesn't work because 2 is not a primitive root mod 17. So we go back to our list and we cross off 17. Let's try p equal 19. So 2 is congruent to 2. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. Well, 19. 19 minus 1 is 18. What are the divisors of 18? 1, 2, 3, 6, 9, and 18. So 2 does not have order 1, 2, or 3. Let's see. 2 to the sixth. What is 2 to the sixth? 64. Mod 19. This is congruent to 7. Mod 19. What is 2 to the ninth? 2 to the ninth is 2 cubed times 2 to the sixth. That's 8 times 7. That's 56. That's minus 1 mod 19. So 2 does not have order 1, 2, 3, 6, or 9. So 2 is a primitive root. Mod 19. What about 3? 3 to the first power is 3. 3 squared is 9. 3 cubed is 27, which is congruent to 8. Mod 19. 3 to the sixth is 3 cubed squared, which is 8 squared, which is 64. 64 is 7. Mod 19. Because 3 times 19 is 57, plus 7 is 64. 3 to the ninth is 3 cubed times 3 to the sixth. 3 cubed is 8. 3 to the sixth is 7. This is 56, which is minus 1, mod 19. So 3 does not have order 1, 2, 3, 6, or 9. So 3 is a primitive root. Mod 19. So the answer to the problem is 19. Or one answer. That's the smallest prime number for which both 2 and 3 are primitive roots. Any questions about this? I mean, it's very good practice doing calculations, which is important in number 3. Okay. Let's see. That was problem 5. Let's look at problem 10. Well, I'll do problems 8 and 10 because they're related. Problem 8. Problem 8 is just to prove that 2 is a primitive root mod 53. So 53 minus 1 is 52. And what are the divisors of 52? They are 1, 2, 4, 13, 26, and 52. So if a number does not have order 1, 2, 4, 13, or 26, mod 52, mod 53, then it's a primitive root mod 53. So 2 to the first power is congruent to 2, mod 53. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16, mod 53. Let's see. What's another number that might have a small remainder? 2 to the 9th is 512, which mod 52 is minus 8. Mod 52, because 512 plus 8 is 520, which is 10 times 52. See, 2 does not have order 1, 2, or 4. What about 2 to the 13? So two to the 13 is 2 squared times 2 squared times 2 to the 9th. 4 times 4 times minus 8. That's 4 times minus 32, which is 4 times 20, because minus 32 is 20 mod 52. That's 80, which mod 52 is, I guess, minus 24, because 2 times 52 is 104. So it's 2 to the 13 is minus 24. Mod, oops, I think I did something wrong. Let me just double check. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. Because I'm looking at these not modulo 52, but modulo 53. So 2 to the 9th is 512. $512 is minus 18. Mod 53, because 512 plus 18 is 530. So 2 to the 13 is 2 squared times 2 squared times 2 to the 9th. That's 4 times 4 times minus 18. 4 times minus 18 is minus 72. 72 is 19 mod 53. So this is 4 times minus 19, which is minus 76 mod 53, which is 106, which is, I think, 30 modulo 53. So 2 to the 13 is 4 times minus 18, or 4 times minus 72, or 4 times minus 19, or minus 76, or 30. Let's see, maybe that's correct, but something still doesn't look correct. Two to the 6th is 64, which is 11 mod 53. 2 to the 12th is 2 to the 6th squared, which is 11 squared, which is 121, which is 15 mod 53. So 2 to the 13th would be 2 times 15, which would be 30. Mod 53. So this is correct because I did it 2 different ways and I got the right answer. 2 to the 26th is 2 to the 13 squared. That's 30 squared, which is 900. If you divide 53 into 900, what do you get? 7 3s are 21, 370, and minus 1. So 900 is congruent to minus 1 mod 53. So 2 does not have order 1 or 2 or 4 or 13 or 26. So it must have order 52. So this is a proof that 2 is a primitive root mod 53. And problem 10 says, find all solutions of 2 to the x congruent to 22 mod 53. So if 2 to the x is 22 mod 53, if we let the index of 22 with respect to the primitive root 2 be equal to k, then x is going to be equal to k. X is going to be congruent to k modulo 52. So if we can find the index of 2 mod of 22 mod 53, then we know all solutions of this exponential congruence. So we have to compute the index of 22. So what's the smallest positive power of 2 congruent to 22 mod 53? And actually, that's not so hard because I already did a lot of calculations. And here I showed that 2 to the 6 is congruent to 11 mod 53. So 2 to the 7th, which is 2 times 2 to the 6th, is congruent to 2 times 11, is congruent to 22 mod 53. So the index of 22 is equal to 7. So x is any number congruent to 7 mod 52. That's the solution to this. Okay. I mean, all of these problems are of exactly the same type. And this is the only thing on the final exam that was not covered in one of the previous midterms. So I think I will stop at this point. I will be having office hours over the next week and a half. So if you have questions when you're going through the reviews, that is the place to log in and ask questions. Anything else before we stop?
Okay, thank you.
All right. Bye all.
I'm the only one here? Oh, yeah.